So with that, Patrick, the floor is yours. Tell us about this project in the Netherlands.
All right, thank you very much, Gerald. Probably you can hear me now. Technical problems are solved at my side.
Yes, sir.
Thank you very much for your flexibility, and also to Dustin and Devon for filling in for me. So my presentation will take you to the Netherlands, tiny country in Western Europe, where Gerald and myself are at this very moment. Pilot testing on a tight schedule. Probably after hearing my presentation, you will tell me, Patrick, you should have arranged it in the other way around, and it will have saved you a lot of money, and even more people, a lot of stress and sleepless nights. But probably next time we will do it in other order, and indeed increased testing will save money. I will give you a very brief introduction to my company, because we are far away. Yes, now we have control. I'm a board member of Groep. We are market leader in the Netherlands, but as you see the figures, we are only a smaller company compared to what you're used to worldwide, and in the US especially. We are a conglomerate of multiple piling companies, of which you see the names in the middle line. On the left-hand side, you see we also have our steel workshop, where we do our welding, and we have our own engineering agency where we do our design, site engineering, technical support. And on the right-hand side, you see our business unit focused on international projects and on equipment trade. The project that I will tell you about is in the north of the Netherlands, a very small town called Bedum. That's where we construct a railway underpass in a meadow, actually. Our national strategy to increase road safety makes us replace level railway intersections by underpasses. And these underpasses obviously have to cross an existing railroad track, so it's made by state construction during multiple train-free periods. And those train-free periods are then during a weekend, so no detours, just no trains for 24, 36 or even 72 hours. Those are replaced by coaches, so traveling during the period will take much longer. And well, the promise of the contractor is trains have to be back on track by the rush hour of Monday morning, and otherwise, well, they will get huge claims for logistics problems, more coaches, and loss of time and turnover by companies who depend on it. This is what a typical level railway intersection can look like in the Netherlands. And this is what we would like to, well, to make in future. So what you also see is, you see that the road is separated from the bicycle lane, so safety increases much in this case. The rail deck foundation that you just saw on the artist impression is bearing on 2 abutments with 8 screw injection piles with a length of 75 feet each, and 2 intermediate piers with 12 screw injection piles each to even 101 feet. For those who have never heard of this screw injection pile system, It's quite common in the Netherlands and Germany. In this case, we use a steel tube with a well-done lost drill head, but we also make these piles with a temporary casing, which is extracted after pouring concrete in situ. But in this case, a lost steel casing with a diameter of 30 inches and a drill head of even 38 inches. We use grout injection during installation as lubricant during installation and to improve the bearing capacity of the steel casing. The soil conditions in this particular project are quite different from what we used to in the Netherlands. In the Netherlands, most construction projects are in the west of the country, close to the sea, actually in one big river delta, where we have very soft clay, the Holocene layer on a Pleistocene sand layer. Pleistocene sand layer offers bearing capacity, and that's what all the engineers know. They know how to deal with it, and they know how piles perform in that particular layer. However, in this area, when you look at the cone penetration test diagram, you see from 13 meters below surface, you see over consolidated stiff clay. We know it is pot clay. This gives a whole other approach to bearing capacity, but in the Pleistocene sand layer, which I mentioned, we look at end bearing of piles and high friction ratios close to the pile tip. And in this particular case, well, we forget about end bearing, and we all have to get this bearing capacity from shaft friction, but we don't know so much about this pot clay bearing capacity. So we have, well, a good couple of tests, but they are all very old. Statistically, they are, well, much away from each other. So we have kind of safe values in our code, and it's not common practice to do pile tests in projects in the Netherlands. We are very much dependent on our design methodology based on cone penetration tests. Well, also these pile lengths, which I presented, 31 meter, it's rather long for what we are used to. So luckily for this project, we had some training before we had to install piles during those train-free periods. If you look at this design drawing more carefully, you see a safety zone A in the middle, which I now point out with the cursor. You see a small safety zone B. And you see that there are even some piles outside of these safety zones. Those 20 piles inside safety zone A are in the middle of the rail tracks, so they can only be installed during a period where there are no trains and when actually the rails is taken out. And after this period, the rails will be placed back in order to let the trains run. During one train-free period, we install the piles. Tracks are brought back in place. After the train-free periods, the train will be back in service, and in the next train-free period, a rail deck will be placed. And after this, well, the new rail tracks are in place, but the underpass will be excavated underneath the new rail deck. So what I said, some training. The 20 piles which are outside of the safety zone, and actually 12 are outside of all safety zones, can be installed with the tracks in service. 8 piles which are in safety zone B can be installed with some extra safety measures, but with the trains in service. Which meant that we could test our performance of installation before we were on this tight schedule of a train-free period. Well, this is when we first found out test piles would have been a good investment, because some of those training piles took over 6 hours. Well, we only budgeted for 2 hours. Yeah, that's a pity as a contractor. However, that's your own money, but not making it in a train-free period, that's a real problem. The probable cause of these disappointing installation results were the limited effect of the cement grout in clay. Normally we use cement grout in sandy layers, and it helps us as a lubricant to screw those piles to the design depth. And the same case for these lost drill heads which you just saw. Those seem to be less effective in clay. Another factor was because these piles with those 30-inch tubes and 37-inch drill heads tend to start floating when they reach a certain critical depth. This was not looked at by the engineers beforehand. It's not that the piles come out, but at a certain moment the uplifting force tends to be higher than the pull down force of the piling rig, so you don't go anywhere. So normally you use a grout with a low water binder ratio in order to have a high cement content, which gives your mixed in place mortar that you create during installation some strength. You take it as an interface with actually, so you can take into account a larger diameter in your design calculations. In this particular case, the grout was only working against us during installation, and even since the water could not drain properly in the clay, we were only pushing the pile up extra next to the floating problem after reaching critical depth. The limited effect of the drill head teeth in clay. Well, we found out during installation that the clay was clogging underneath the drill head between the teeth, and well, we get a bulb of clay underneath this drill head, and the teeth were not effective anymore. And normally in sands, they just cut through the sands, spread the grout around. Well, and we have a very efficient installation process. About buoyancy, this could have been foreseen. Normally with smaller pile diameters, the weight per area is higher, and you have your rig's pull down force, which is much higher than the buoyancy of the pile. What we normally do when we have large diameters steel tubes with a closed toe. We will fill this with concrete during installation. However, in most cases, we don't have reinforcement over the full length of the pile, so you fill it until the end of your reinforcement cage, so you can place the reinforcement cage only after installation. But in this particular case, we had reinforcement cages over the full length. So in order to fill these piles with concrete during installation, the cages had to be placed also during or even before installation. Because we were looking at pile installation during a train-free period with a cycle time of only 2 hours per pile, we later placed these reinforcement cages in the steel workshops where the steel tubes were assembled. Well, the measures taken to improve installation cycle time in the second training were a decrease of cement content in grout. We discussed it with our client, with the engineers, and together we decided to add some bentonite to the grout, but still with a large cement content. As I just said, placement of the rebar cages in the welding workshop, so no extra works on site. And pouring of concrete we did with concrete pump truck after 10 to 12 meters of driving, so before reaching the critical depth for buoyancy. Well, this is what it looked like, the left-hand picture just before start of the project, and at the right-hand picture, the tracks are taken away, and well, nobody has an idea that there has ever been a railroad track. But on Monday morning, it looks again more like the left-hand picture. Well, all piles were installed successfully in the available time frame. So the trains were running on Monday morning along the tracks that were brought back in place, just on the normal ballast bed that was in place before we placed the piles. So the piles are not yet in function, but they are there for the next construction stage. Well, the next construction stage would be within about 2.5 months. But after evaluation of this first train-free period, we found out when checking the piling logs that there was high water usage during pile installation, low cement usage, bentonite. Well, we use much more, kind of in line with liters of water. Grout density at the start was too low. Grout density halfway the installation process was too low, and finally the grout density at final depth of pile installation was okay. Normally during installation of these type of piles, you have your grout backflow. So probably while reaching design depth, all the grout with low density is already displaced, replaced by grout with a higher density, so with the well, agreed cement content. However, you cannot prove that there is not either a bentonite interface on your steel tube or between the soil profile and your grouted annulus around the pile. So that was a problem. We had a crew who optimized the drill mud during the installation process and well, managed to install those piles on time. but we obviously did not do what we promised. So we discovered at the end of August 2021 that we had this issue. The next rain-free period would be on October 22nd, 2021. So we had 2.5 months to go to prove the piles had the required bearing capacity. Normally, when you have some piles that are not trusted, you can test them, and in that way prove they are okay. In this case, we only had the installation logs that showed we did not do what we agreed. Well, nobody with too much experience with this type of soil, also no consulting engineers, external engineers, or other contractors. Piles were under the railway track, so we could not test them. So we had 2.5 months actually to install sacrificial model piles, to do the testing that we should have done beforehand, well, before the next rain-free period. Yeah, what was above our heads? Scenario 1, the next rain-free period could not be used to place the deck. So you get a change of design, you get a modification of the foundation. If you get a modification of the foundation, obviously more piles, you get modifications to the deck. 2 extra rain-free periods are required. 1 to place the extra piles, and 1 for the deck placement. And you have potential claims between 500,000 euros, so about 550 in dollars, and 1.5 million in euros. You have a lot of reputational damage in the industry. Scenario number 2 was even worse, but actually we were the ones who pulled the brake to not go there, because if our client accepted the piles as they were on a theoretical motivation, we would have risked unacceptable settlement after commissioning of the underpass. Well, risk of severe delay damage, taking the train tracks out of service, potential claims certainly above 1.5 million euros. Severe reputational damage, not only in the industry, and probably an 8 o'clock news item. 2.5 months until the next rain-free period. So it took us 4 weeks, or actually we took 4 weeks for the test setup design, additional soil investigation on the place that was designated for the test piles, immediate installation of test piles, which is then a setup period to get there, to develop the shaft friction during 1 month. After installation of the test piles, together with our client, the contractor, we informed the railway authorities, local authorities, and then we agreed on the test result interpretation protocol. There actually was no time to inform them before, because we knew if we would get into a discussion about this setup, we would for sure not make it in 2.5 months. After 2.5 months, we had 2 weeks for testing and interpretation of the results, and 1 week left. Well, you see a picture of the test setup. We took scaled piles, so 22 inches, with a crowd composition as we found back in the pile logs from the piles installed during the train-free period. So with low cement, much more bentonite, much more water. we had a test set up with 325 metric tons in Kentlet's capacity. And a pile failure load, we found out, was about 200 metric tons. Why then a 325 metric ton setup? Because we could not agree on the actual pile bearing capacity, taking into account all the layers that are there, but do not contribute to the bearing capacity during the surface, but who will definitely interfere your testing. Well, we needed this extra week badly because of strain gauge interpretation. Short story, you can never have enough strain gauges because some went out of service. There was some discussion about the trajectories below the strain gauges that could have divided better if we used more strain gauges. In the end, we found a safe best estimate of the load bearing capacity of the pot clay layer, where it was all about, and we ended up with an acceptable less than 8% underperformance in relation to the design values that were earlier chosen. We had about 8% left in our safety factors, so we saved the day. Then I want to show you this video, because this is what happened during the weekend from Friday 22 October until Monday morning 25th of October. You see on the left hand side, which I point now out with the cursor, the new railway deck. The excavators already took out the tracks and the whole railroad. The rail deck is pushed into place, and the test train runs. Well, thank you very much for your attention.